So good evening, everyone. Thanks so much for joining us tonight. I'm Tara Despo. I'm a water resource specialist with the Ministry of Agriculture and Food, and I'd like to welcome you all to our Hydrology 101 public webinar. Before we begin, I would like to acknowledge that I'm speaking to you today from the traditional and unceded territory of the Stolo people, the people of the river, specifically the Matski and Sumas First Nations, whose ways of life have been deeply connected to waterways in the area for time immemorial. Now, tonight's webinar will aim to provide a foundational understanding of hydrology, the science of water. We'll be exploring key concepts like the water cycle, how water moves through watersheds, and the factors that influence stream flow across British Columbia's diverse landscapes. This information is particularly relevant to our agricultural community, as understanding the science of water and how it moves can help inform and strengthen water management planning and on-farm decision-making. We're very fortunate to have Natasha Cowie with us this evening. Tasha is a hydrologist with the BC River Forecast Centre and previously worked as a hydrologist and manager with Hatfield Consultants. Tasha is a professional hydrologist and holds a Master of Science in Physical Geography from the University of British Columbia, with a research focus in proglacial stream hydrology and geomorphology. We're happy to have her with us today to share her in-depth knowledge from over a decade of experience in monitoring and assessing hydrological conditions in BC. So thanks again for joining us. And now I'd like to hand it over to Tasha to begin her presentation on Hydrology 101. Go ahead, Tasha.
Wonderful. Thank you so much. I'll get the screen share started. Wonderful. Hello, everyone, and welcome to Hydrology 101. My name is Natasha Cowie. I'm a hydrologist with the BC River Forecast Centre. I'm located in Victoria, the traditional territory of the Lekwungen people, today known as the Songhees and Esquimalt First Nations. Thanks to all of you for being here this evening. It's a pleasure to be speaking to you. This presentation will be an introduction to hydrology with a focus on the unique aspects of BC's water. We'll cover three main topics: an overview of hydrological processes, a more specific discussion of BC's weather and climate and how they drive water availability, and a description of the different patterns of BC's rivers across the province and over time. Finally, we'll conclude with an overview of online resources about BC's hydrology. We'll begin by going over a few fundamental definitions, starting with hydrology itself. Hydrology is the science of the Earth's water. It covers water distribution, movement, and properties through all phases and pathways of the hydrologic cycle or water cycle. Hydrology includes water in all forms, above or below ground, frozen in ice and snow, and suspended as water vapor. Water cycles from the Earth's surface to the atmosphere and back in the hydrologic cycle, also called the water cycle. As we all might remember from elementary school and tours of science museums, water covers 75% of the Earth's surface in liquid and frozen form. Oceans store 96% of all water on Earth. Water is everywhere, even though it may not be immediately obvious to us. All water is in constant motion across our planet. Water's journey through the hydrologic cycle can be very short, less than a day, or over 1 million years when water is locked up in the depths of Antarctica's ice or deep groundwater. Sometimes even longer. In 2013, researchers found billion-year-old groundwater beneath the Canadian Shield at a mine near Timmins, Ontario. The key components of the hydrologic cycle include precipitation, water released from clouds in the form of rain, freezing rain, sleet, snow, or hail. Evapotranspiration, water evaporated into the atmosphere from the soil and water bodies and transpired from the soil to the atmosphere through plants. Runoff, the flow of water over the land's surface, and storage, which includes lakes and wetlands, groundwater, snow and ice, and oceans. Watersheds are areas that collect water and direct it to a defined outflow point called the watershed outlet. To define a watershed, pick the point of interest first, so the mouth of a river, a gauging station that measures stream flow, or a dam, then look upstream to the drainage area that contributes water to that point. The boundaries of watersheds are the high points of land that split the direction of surface runoff. Watersheds are fairly easy to identify in the mountains, but they can be much more challenging to identify in flatter terrain. For example, the satellite image on the right shows the watershed corresponding to the Water Survey of Canada station, Big Creek below Graveyard Creek. Most of the water that falls or melts within the blue lines will eventually converge at the gauging station, which in this example has been defined as the watershed outlet. Alternately, the outlet could be defined as the mouth of Big Creek, where it enters the Chilcotin River, which is far downstream, not pictured in this image. If the outlet was defined as Big Creek at the mouth, the watershed would be much larger. Changes that occur within a watershed, such as logging or wildfires, can be reflected in the patterns of flow at the outlet and potentially even further downstream. Groundwater aquifers are part of watersheds, but their boundaries aren't necessarily the same as those for the surface. There can be multiple aquifers within one watershed, or aquifers can span multiple watersheds. To fully understand what's going on in a river or stream, it's essential to understand the characteristics of its watershed. Watersheds vary widely in size, depending on where the outlet point is defined. Smaller watersheds are also referred to as drainage basins or catchments, and larger watersheds are often called river basins. So if we define a watershed outlet point as, say, the mouth of the Fraser River, where it enters the ocean, the watershed is massive. The whole area of land that contributes water draining to that point covers 240,000 square kilometers, about a quarter of the entire province. The map on the right is from a 2018 study. It shows the overall Fraser watershed and 4 of its sub-watersheds. Watersheds are nested into each other, smaller into larger. For example, the Quesnel River watershed is a sub-watershed of the Fraser. It's about 12,000 square kilometers, and it contributes about 9% of the average yearly flow of the Fraser. But watersheds can be much, much smaller, even just a few square kilometers or less. The size of a watershed affects how it responds to runoff events, such as rainstorms or big increases in snowmelt from hot weather, and also how sensitive it is to land disturbances like wildfire. Small watersheds tend to be flashy, meaning that they respond very quickly to these events. The water from rain or snowmelt flowing over the surface gets to the stream channel fast, and you see rapid increases in stream flow, followed by rapid decreases as soon as the rain or the melt slows down. They're also usually sensitive to disturbances, meaning that changes caused by these disturbances are often fairly easy to detect in stream flows. In contrast, large watersheds are generally slower to respond to runoff events, and because they cover so much land and tend to have a lot of landscape variability, runoff is not as closely tied to stream flow because there is a broad range of travel times and pathways for water to get from the widespread areas of the watershed into the stream channel. The water balance equation is used to numerically define water inputs and outputs to a watershed or other area of interest, such as a mine site or a farm. The water balance consists of inputs, so mainly from precipitation and groundwater moving into the watershed, outputs, evapotranspiration, stream flow, and groundwater moving out of the watershed, and storage. So this can be in the form of soil moisture, aquifers, lakes, ice, and snow. The general equation pictured here on the right-hand side uses the term Q to represent surface runoff. P is precipitation, ET is evapotranspiration, and delta S is the change in storage. Water balance equations can be a lot more complex than the general equation presented here and may be arranged in different ways, but the fundamental principles remain the same. Knowing all the components of the hydrological cycle within a watershed can help determine a water balance to understand various processes, including the main factors that drive stream flow patterns and water availability over space and through time. Stream flow is also referred to as discharge or runoff, and as noted earlier, is often represented by the term Q. It is the volume of water flowing past a reference point, such as the outlet of a watershed, over a specific period of time. It's usually expressed as cubic meters per second. Stream flow regimes, or the timing and duration of high and low flows, depend on the main forms of precipitation and storage in a watershed. We'll talk more about BC's stream flow regimes later in the presentation. The Water Survey of Canada, WSC, is the primary agency responsible for measuring stream flows in Canada. It maintains a nationwide network of hydrometric stream gauges, there are hundreds in BC, provides publicly accessible data, and sets measurement quality standards. The photos on the right are of the WSC station Bulkley River near Smithers. They were taken in late June of last year when the river was at its annual peak. The inset graph is a screenshot from the WSC's public website showing the stream flow, which is the orange line, and the water level, the green line, over the 3 months leading up to the annual peak. So this is April to June of 2024. In BC, establishment of a new provincial hydrometric network is underway. This network is intended to fill gaps in areas that are not covered as well by the WSC network, such as smaller streams. The WSC primarily focuses on rivers and larger systems. Stream flows over any time period can be tracked by a hydrograph, literally a water graph. The shape of the hydrograph, called the hydrologic response, is directly connected to the weather, the precipitation amount, duration, and intensity if it's rainfall, or in the case of snowmelt, the air temperatures, as well as the characteristics of the watershed, such as its size, land use, and pre-existing conditions such as soil saturation. In this example on the right of the peak from a single storm event, the bar graph at the top shows hourly rainfall totals from a storm. The lower line graph is the corresponding hydrograph showing streamflow over the same time period. Streamflow begins to increase after a rainstorm or snowmelt starts. This increase is called the rising limb of the hydrograph. The maximum streamflow in response to a storm or snowmelt is referred to as peak flow. The time from the center of a rainstorm to the peak in streamflow generated by that storm is called the basin lag, or simply the lag time. After a storm or snowmelt ends, contributions to streamflow decrease and the hydrograph begins to decrease as well, called the falling limb. Note at the bottom the base flow contributions sustaining streamflows in this example, hydrograph. This is the groundwater component of the flow, and we'll come back to base flow shortly. The last slide showed a generalized example of an event hydrograph, the hydrograph for a single storm. But hydrographs can cover different time periods. Often they're shown as annual hydrographs. This example is the Similkameen River at Princeton at the water survey gauge 08NL007. They're all referred to by these alphanumeric identifiers. The picture was taken at Bromley Rock Provincial Park. Measurements at the station started in 1914, but the data record isn't continuous until 1939. Still, this is a respectable period of record at more than 80 years. The solid gray line on the graph shows the long-term median flow for each day of the year. The median is the central value in a data set. So for each day of the year, this line shows the middle value out of all those 80+ data points. The dashed blue line shows the maximum recorded flow for each day of the year, and the red dashed line shows the minimum recorded flow on each day of the year. Daily flows for the year 2023, used as the example here, are plotted in light green. The Similkameen receives a lot of its water from melt of the seasonal snowpack. Its annual peak usually occurs in late May or early June. You can see that on the gray line. But the river sometimes experiences high flows in the fall and early winter as well, due to large coastal storms, atmospheric rivers, that extend into the interior. The lowest flows usually occur in the middle of winter, when precipitation is being temporarily stored as snow, and in the summer and early fall in the dry season. In this example from 2023, the photo was taken on April 21, just before flows started increasing in response to snowmelt. In 2023, the high flow season from spring melt, called freshet, occurred much earlier than usual and had two nearly identical peaks that were generated by 2 May heat waves, causing a double pulse of snowmelt. The seasonal snowpack was depleted early because of this, and there was very little rain in summer 2023, causing extremely low flows, coinciding with an extended period of severe drought across much of the province. In the fall, coastal storms began to recharge the flows slightly, and flows eventually got a larger boost from a sizable atmospheric river in early December. The connectivity of groundwater to a stream can be complex, but most simply, we can think about groundwater as either being disconnected or connected to a stream. Groundwater is stored in two forms: the unsaturated zone, which you can see near the surface, that's as soil moisture, and the saturated zone deeper below ground in the underlying sediment or bedrock. In general, if the water table or saturated zone is well below the stream is considered to be disconnected from the aquifer, as you can see in the two examples on the left-hand side. However, even though the stream may be referred to as disconnected, there can still be some loss from the stream to the water table. In this scenario, it's referred to as a losing stream. Disconnected streams receive all of their flow from surface runoff only. They aren't sustained by groundwater, so if there's no surface water coming in, they go dry. Keep that in mind for the next slide. If the water table intersects with the stream channel, then it's considered to be connected, as in the two examples on the right-hand side. In these situations, the stream can be a gaining stream or a gaining reach. A reach is a section of stream channel, if groundwater is contributing water to the stream. This groundwater contribution is called base flow. Similar to disconnected streams, if water from the stream channel in a connected stream is moving into an aquifer and recharging the groundwater supply, it's referred to as a losing stream or a losing reach. It gets even more complicated than these diagrams suggest. Gaining and losing reaches may switch during the seasons with changes in seasonal precipitation and water levels, and it's common to see both gaining and losing reaches on the same stream in the same season, just a short distance apart. Knowing the influence of groundwater on stream flow is important because it gives us an understanding of when and where we can expect water to be available. Streams can be classified into 3 different types based on their relative degree of groundwater influence, which in turn dictates their flow duration, the length of time that a stream sustains visible, measurable surface flow. Perennial streams typically have water flowing year-round, as you can see in this example hydrograph on the left. The water comes from surface runoff, precipitation and snowmelt, as well as groundwater base flow. This picture of Driftwood Creek in the Babine Mountains east of Smithers was taken in June when the stream was receiving plenty of runoff from high elevation snowmelt, as well as recent rainstorms. The stream has a well-defined vegetated channel with obvious banks. Intermittent or seasonal streams have flow during certain periods of the year when there's sufficient water flowing from storms, snowmelt, and base flow. During dry periods, intermittent streams may not have flowing surface water, but there may be pools of water visible, as in this photo of Perseverance Creek on Vancouver Island. Water may be moving subsurface among the gravels of the stream bed. Perseverance Creek has a clearly defined channel, and as this picture shows, the sand and gravel in the channel are sorted, meaning that they have been organized by size by the movement of water. And this indicates that there's a considerable flow volume sometimes, enough to move rocks around. But in the summer, portions of the creek may go dry on the surface. Finally, ephemeral streams flow only after precipitation and dry out in between precipitation events. They do not have any base flow from groundwater. This picture taken in a forested park on southern Vancouver Island shows a dry depression in the ground surface covered in twigs and leaf litter. It collects water at some times of the year, in the fall and winter wet season, but goes completely dry in between rain events. Intermittent and ephemeral temporary streams often form the headwaters, the starting point of the perennial streams lower in a watershed. So they are fully a part of the whole stream system, even though they aren't always obvious. Temporary streams provide important habitat for many species. They supply water, sediment, and nutrients to downstream systems. They can also supply pollutants or excessive sediment to downstream. Like everything else in a watershed, they are connected to everything downstream and are critical to the health of the overall river systems. Now that we've gone over the fundamental processes of hydrology, we'll move into a discussion of the numbers that we use to describe characteristics of stream flow. Hydrological indices are used to describe and compare different river systems. They can also be applied to other things that affect hydrology, such as precipitation or snowpack. When we describe a stream with numbers, we have a lot of choices, depending on the questions we need to answer. Do we want to know the average flow over the entire year or during a specific season? Or do we want to assess flood and drought hazard? If we're describing the typical or normal flows over a period of time, like a year or a season, we use mean or median. The median is the midpoint, the middle value of a set of numbers. It's usually at least slightly different from the mean or average for the same set. The median can provide a more accurate indicator than the mean of the true center of a range of data because it's less affected by extreme values called outliers. So you'll often see mean annual discharge, MAD, referred to in hydrology. It's simply the average flow over a year. The map shows current streamflow conditions on April 1st, 2025 as percent of MAD. Since this example is from the early spring, many rivers are at pretty low percent MAD, but some of the coastal and southern interior rivers are at or above 100% thanks to recent precipitation and snowmelt. The hydrograph, which is the location starred on the map, shows the maximum, minimum, and median daily flows for the West Kettle River. And that's alongside the MAD, which is the dashed green line. And so as of April 1, the river was flowing at about 70% of MAD, and you can see that in that black line. Maximum and minimum indices characterize extremes. For example, peaks are important for understanding flows that are high enough to change the shape of channels and cause flooding, while lows are important for defining drought conditions and environmental flow needs, such as the minimum flows that fish need. When we evaluate specific high or low flow events, it's important to also know the context of intensity, duration, and frequency. How high or low was the event compared to the typical patterns of the river? How long did the high or the low flow period last? Duration is especially important for assessing drought and water shortage. And how often do events like this happen in our river of interest, and what can that tell us about how likely they are to occur again? Return periods are a way to estimate how often a specific high or low flow level will occur. They're expressed in terms of years, for example, a 50 or 100-year flood. Using a time period can help provide us with a frame of reference for how extreme a big event actually is. And we often discuss events in these terms because it makes them easier to imagine and visualize. However, return periods can give the false impression that these events go in cycles and are therefore predictable. So we can use annual exceedance probability, AEP, rather than return period to avoid this implication. For example, referring to a flood as a 1 in 100-year event can suggest that it occurs only once every 100 years. It actually means an event that has a 1% probability of occurrence in any given year, or AEP. So a 1% AEP flood means the same thing as 100-year flood. The pictures on the right show a couple of examples of rivers at different approximate return periods. And return periods are often used for flood hazard and engineering design purposes, so it's important to keep in mind, as the note at the bottom indicates, these pictures are just intended to be general examples. The flow levels shown in these photos haven't been confirmed to correspond to a particular return period for these rivers. The top photo is a river near Squamish after a large storm event in January 2024. At the time the photo was taken, flows were high, but they still appear to be contained by the banks of the river. This is about what would be expected for a lower return period flow, a 2-year flow that has a 50% chance of occurring any given year. So you'd expect it to be a pretty average peak. By contrast, the bottom photo was taken in June 2016 during a major flood event in the Peace region caused by a large rainstorm. Flows in some rivers exceeded the 100-year return period, causing damage to roads, bridges, and hundreds of homes and businesses. These big flood events are usually pretty rare, with a low chance of occurring any year. But just because they occur one year doesn't mean they won't occur the next as well. And it's important to remember that return periods can change because each new high or low flow event that occurs increases our understanding of how often the events happen. The data pool grows. So we've talked a lot about hydrology in general terms, but we can't really talk about the hydrology of a specific place without also talking about the weather and climate of that place because they are a dominant influence on hydrology. And before we talk about BC's weather and climate, we'll look at what those two terms actually mean. The terms are sometimes confused with one another, even though they mean different things. One way to look at this is that climate is what you expect, weather is what you get. Weather refers to specific conditions of the atmosphere at a specific place and time. So for example, the weather in Prince George as of 9 a.m. on the morning of April 3, 2025 was sunny and -1. And the Environment and Climate Change Canada weather forecast for the next week shows a lot of warming and mixed sun and clouds with some rain on April 7. Weather is short term, what we actually experience day to day. Climate refers to what the weather is like over a long period of time, for a larger area. To describe the climate, we look at averages of weather, things like precipitation, temperature, sunshine, and wind. Often 30-year averages called normals are used to define the climate. Normals are usually updated every 10 years because the climate shifts over time. This graph shows Prince George temperature and precipitation climate normals by month for the normal period from 1991 to 2020. The temperature on April 3, if you look up at the top, is forecast to reach 8 degrees Celsius, a bit lower than the normal daily maximum for the whole month of April, which is 11 degrees Celsius. Total precipitation for the month of April averaged about 37 millimeters over the normal period. Looking at the normals chart, we can see that April is usually one of the lower precipitation months for Prince George. The highest precipitation totals usually occur in early summer and fall. A bit more discussion about climate before we talk specifically about BC. Climate is always shifting in complex ways, and this graph is a way of visualizing the different patterns that are all going on at once with climate. The green line in the graph represents short-term climate variability. So these are cycles that shift back and forth on the time span of years to decades. One example is INSO events. INSO refers to the El Niño Southern Oscillation. INSO cycles are caused by large-scale ocean-atmosphere interactions. There are three phases: El Niño, La Niña, and the in-between neutral conditions. The phases usually last about 6 to 18 months. In BC, we usually notice the INSO effects on weather in the winter and spring, which tend to be warmer in El Niños and cooler in La Niñas. The orange line represents medium-term cycles operating on a scale of decades. A key example is the Pacific Decadal Oscillation, or PDO. It's like INSO. PDO is caused by ocean-atmosphere interactions, but it has a longer time scale, cycling over periods of about 20 to 30 years. Also like INSO, it has warmer and cooler phases, and it's a strong influence on BC's weather. And the blue line represents climate change itself, large-scale, long-term trends or major shifts in climate that take place over decades to centuries. Because all these climate fluctuations are happening at the same time, it can be very difficult to figure out what is going on over the long term. This is why very long-term data sets are used to assess climate change. You need to look at a lot of years of data to be able to figure out how things are changing over long timescales. And it can also be challenging to determine the true effects of changes at the watershed level, such as forestry, wildfire, or water allocations, because climate patterns can be strong enough to mask them. For example, if we see higher stream flows in a watershed for several years after it is logged, is this due to the logging or due to more snowpack as a result of a cooler PDO phase, or both? So to assess what is really happening in a watershed, it's important to know the climatic context. So now let's talk about the climate in BC. The climate pattern overall is for winds from the Pacific Ocean to flow eastward across the province, interacting with the numerous mountain ranges and basins. This interaction between mountain ranges and dominant wind flow pattern creates a series of wetter windward climates and drier rain shadow climates across the province. So, as a result, BC has highly variable annual precipitation, as seen in this map, showing mean annual precipitation for the 1961 to 1990 climate normal period. It ranges from a low of less than 200 millimeters a year to over 8,000 millimeters a year. The wet season for the coast is the fall and winter, while much of the interior gets most precipitation in the spring and early summer. And snow is a big factor for almost the entire province, generally accounting for 25 to 75% of annual precipitation, except for some lower elevation coastal locations. Temperatures also vary widely across the province, with mean annual temperatures ranging from minus 14 degrees to almost plus 14 degrees over this 1961 to 1990 period. Along the coast, temperatures are more consistent year-round and averaged over the year, generally warmer due to the moderating influence of the ocean. But in the interior, there's much wider temperature variation. Temperatures also vary by elevation, topography, and latitude, how far north or south a location is. So here's a couple of examples to illustrate differences between the coast and interior, using these 1961 to 1990 normals, the same as the maps. Kelowna, in the southern interior, received average annual precipitation of 366 millimeters over this time period. About 29% of this precipitation fell as snow. Average annual temperature was 7 degrees, with monthly averages ranging over a span of 21 degrees, from minus 2 to plus 19. The climate for Bamfield along the south coast is much different. During the 1961 to 1990 normal period, Bamfield averaged 2,876 millimeters of precipitation annually, of which only about 1% fell as snow. The mean annual temperature was 9 degrees, And monthly averages were consistently above freezing and did not get as high as Kelowna's, ranging from +4 to +15, a span of only 11 degrees, much less than Kelowna's 21-degree range. So what shifts in climate patterns might we see in BC with ongoing climate change? In general, long-term trends indicate warmer air temperatures year-round, particularly in winter, and increases in precipitation year-round, although this is highly variable across the province. These two maps on the right-hand side show 1900 to 2013 average annual temperature change in degrees Celsius per century, which is plus 1.4 degrees for the province as a whole, and average annual precipitation change as percent per century, which is plus 12% for the province. We're also likely to see an increase in the frequency of extreme weather events, potentially meaning more frequent droughts and flooding as a result. This goes back to the idea of return periods that we talked about earlier. For example, a very low flow level for a particular river that used to have a 100-year return period or 1% chance of occurrence might become a 10-year return period or 10% chance of occurrence. And we can expect to see changes in the short and medium-term cycles of climate variability as well, such as more frequent shifts between the warm and cool phases of INSO and PDO. And finally, we're going to bring the focus from BC's climate and weather to BC's hydrology. Hydrologic regimes refer to the different seasonal patterns of rivers. We have four main hydrologic regimes in BC: rain-dominated or pluvial, snow-dominated or nival, ice-augmented or glacial, and hybrid or mixed regime, which can vary widely. In rain-dominated regimes, also called pluvial regimes, streamflows closely follow the seasonal patterns of rainfall. Pluvial regimes are mainly located along the coast. This example is the San Juan River on the west coast of Vancouver Island, the location that's circled on the map. The hydrograph on the upper right is for the Water Survey of Canada station on the river, including all historical data going back to 1959. The different colored bands represent the historical data, color-coded by percentile ranges. And percentiles are just a way of ordering data based on how the values are distributed. The takeaway here is that the darker shades of blue and purple indicate the higher historical data ranges, and the brighter shades of yellow to red indicate the lower ranges. The green band represents the average range for the river. It's hard to see, but there's a gray line running through the middle of that green band. That represents the long-term median. And the next several slides will all show hydrographs in this same format. Pluvial regimes tend to be very flashy. The watersheds and rivers respond quickly to rainfall events. Typically, the peak flows in rain-dominated systems tend to occur in the late fall and winter as strong storm systems move onto the coast. The dry season is in summer and early fall as high-pressure systems direct precipitation away from the coast. There's little to no influence from melt of seasonal snowpack. Although rain-on-snow events, when rain falls on top of snow and melts it very quickly, can have a major influence on peak flows. Snow-dominated regimes, also called nival regimes, mainly occur in the interior plateau and the coast and interior mountain ranges. This example hydrograph for the North Thompson River shows the distinct snowmelt-driven peak characteristic of nival regimes. The photo is of the confluence of the North and South Thompson Rivers. It was taken in March when flows were still low, right before freshet, that spring high flow period that's generated by snowmelt. In nival regimes, winter precipitation mainly falls as snow and remains in storage until spring melt. Flows tend to be low through winter, as well as in late summer and fall. High flows are typically between April and July, but can occur earlier in the year, depending on snowpack conditions and weather. Ice-augmented or glacial regimes are generally similar to nival regimes, but in glacial regimes, streamflows in the summer season get a boost from the melting of glacial ice. Glacial influence typically shows up when the basins have at least 2 to 5% of their watershed area as glacier cover. So the coast, Columbia, Rocky Mountain ranges are where you see this kind of basin. The example shown here, Bridge River below Bridge Glacier, has a very strong glacial influence with approximately 58% basin glacier coverage. Peak flows in glaciarized basins typically occur later than those in snow-dominated systems due to the colder climates. Summer low flows tend to be less severe due to meltwater inputs from the glaciers, which generate a sustained higher flow season during summer, sometimes persisting into early fall. In addition to buffering flows, glacial meltwater also has a temperature regulating effect, helping to keep water temperatures cooler even in the summer heat. Despite their high elevation, glacial systems may also be affected by rainstorms. For example, the record peak recorded flow at this location on Bridge River was caused by a 1984 rain event, which likely included a rain on snow component that amplified runoff. Extreme high flows in glacial systems may also be caused by glacial lake outburst floods when a natural dam formed by sediment or ice bursts. Hybrid systems, also called mixed regime systems, vary widely. We'll go over two examples, one from the coast and one from the interior. Hybrid regimes are a combination of pluvial and nival regimes containing elements of both rain and snowmelt, and sometimes ice melt. They're common in coastal and near coastal regions where the uppermost portions of watersheds are sufficiently high elevation to accumulate a seasonal snowpack, but the lower elevation portions of the watershed receive a substantial proportion of fall and winter precipitation as rain. The example pictured here is the Chilliwack River. Hybrid regimes are characterized by two annual high flow periods resulting from spring and summer snowmelt and fall and winter rainstorms. Flows are usually lowest in the lower precipitation summer months. Rain on snow events tend to be common in this regime because snow is often stored at elevations where rainfall can also occur during the winter. Hybrid regimes in the interior are similar to those on the coast, but interior systems have a distinct winter low flow period. In these systems, sometimes called mixed convective regimes, snowmelt combined with convective summer precipitation, so those really high intensity summer thunderstorms, often causes the highest flows of the year. Interior hybrid regime rivers are commonly found in the Northeast, like this example of the Sukunka River, where winter precipitation falls almost entirely as snow rather than rain, resulting in very low flows through the wintertime period. Most of the precipitation in these systems falls in the summer as a result of convective storms. Fall rainstorms can also drive higher flows. So how might we see the changes in climate that we talked about earlier showing up in the patterns of stream flows? Because BC is such a large area with so much variation in landscapes, climate, and hydrologic regimes, streamflows will respond differently to climate change in different watersheds and regions of the province. But generally speaking, here are some of the main changes we can expect. Warmer temperatures will mean a higher proportion of precipitation falls as rain rather than snow. As a result, we may see snowmelt-driven nival rivers shifting to rainfall-driven pluvial regimes or hybrid regimes. That will mean higher winter flows because precipitation is going directly into the rivers rather than being stored as snowpack. It will also mean lower summer flows because that water tank provided by the snowpack won't last as long. Because snow will probably melt earlier, due to warmer spring temperatures and just a lower snowpack overall, we can expect earlier and possibly lower peaks in spring freshet, and as mentioned, lower summer flows. So this graph on the right-hand side is a good illustration of these predicted changes. It's from a research paper published in 2019 that investigated potential future changes in flow in the Fraser River. The researchers developed projections of streamflows for two future time periods, the 2050s in blue and the 2080s in red, and compared them to the 1990s in black. And note that this hydrograph is on the water year rather than the calendar year. The water year runs from October to September. It's often used in hydrology because it doesn't split the winter period. It keeps all of the winter period together. The annual peak in the Fraser is driven by snowmelt. If the influence of snowmelt continues to decrease in the future, as researchers expect, the annual peak will get lower and shift earlier. So in this projection, 25 days earlier in the 2050s and 40 days earlier in the 2080s compared to the 1990s. And summer flows will get lower and lower. But we will likely see higher flows in fall and winter because storms will be bringing more rain than snow. You can see that especially in that red line. One of the main challenges with this shift is that we may have less and less water during the summer season when water demand tends to be the highest. Similar to snowpack, we can expect to see large decreases in glacier size. These glacier declines are already underway. Rivers that currently have a large glacial influence will turn into nival or hybrid regimes. Right now, as glacier melt rates continue to increase, we're already seeing higher summer flows in glacially fed rivers. A benefit of this is cooler water temperatures. which can really help fish during the hot summer. But as glaciers get smaller and smaller, summer flows in these rivers will start to decline and water temperatures will come up. It's likely that we'll continue to see more frequent wildfires as a result of climate change. Wildfire-impacted watersheds tend to have higher surface runoff, meaning earlier and higher spring freshet peaks. As a result, flood hazard may increase in watersheds affected by recent wildfires. And a higher frequency of extreme weather events, unusually high or low temperatures or precipitation, or both, means an increase in the hazard of both flood and drought. All of these potential changes in climate and hydrology pose challenges, but the better we understand how things are changing, the more effective we can be at finding solutions to adapt to the changes. And the good news is that we already know a lot about our province's climate, weather, and hydrology, and our understanding is increasing all the time. I've shown a few examples from recent research in this presentation, but these are just a tiny fraction of all the projects and communications that are happening right now to improve our knowledge about BC's hydrology and to better share that knowledge among all of us who live and work here. And I'll conclude with a few slides highlighting key websites that provide resources for the application of hydrological sciences to real life. Starting with one that you're all likely very familiar with, the AgriService BC website, which provides a wide array of tools and services and can help connect you to programs, resources, education, and events. A few examples of the many resources provided are shown on the left-hand side of this slide. And in particular, I want to highlight the AgriService BC's regional newsletter for the latest news on programs, events, and resources in your region. And you can sign up with this link circled on the right-hand side. And another one of the resources that you'll find on this portal is the Drought in Agriculture website, which is linked from the Environmental Emergencies and Droughts section. And I will show that one next. So the Drought in Agriculture website is a starting point to access a broad array of resources to help manage drought impacts. So for a fast overview, you can start with the quick guide to drought resources. That's linked at the top of the page. It's circled there. It's a 2-page PDF summary. The first page of that is shown on the far left. A couple of other tools that I've highlighted here among the many available on this website are the BC AgriWeather and Evapotranspiration Calculator, and the 2 screenshots on the lower left are from this tool, as well as the BC Agriculture Water Calculator, the top screenshot. And this helps estimate the annual irrigation or livestock water demand for a farm. And it also now features a dugout calculator designed to help producers plan for their water storage needs. The Drought Information Portal is intended to be a one-stop shop for information on drought conditions and resources across BC. On the portal, you'll find current and historical provincial drought levels, watershed conditions, and other information related to drought monitoring. Through the portal, you can access interactive maps of streamflow conditions and low flow forecasts, precipitation, groundwater, and snowpack conditions, and information about regulatory measures such as angling closures and local water restrictions. And finally, my own agency's website, the River Forecast Center, analyzes snowpack, assesses seasonal water supply and flood risk, and predicts flows in BC's rivers. On our website, you can access information about current flood warnings and advisories, hydrological forecasts and current streamflow conditions, and during the winter and spring seasons, so right now, the snow survey and water supply bulletins and maps. And that concludes this evening's presentation. Thank you all so much for attending. We'll now stop the recording and go to questions.